Each of these letters represents one of the classic locations for Strat square. Skin, anus, vagina, esophagus, and mouth. All of these organs are organs that are subject to friction. And so, a Strat square positioned along the line of these organs can provide for protection. So it's found in locations that are subject to friction or attrition. For instance, on the surface of the skin, we constantly scrape our, even doing this, we're scraping off some surface cells. Well, it's okay because we have a thick layer, maybe 30 or 40 cells thick, along that surface epidermis. And those lost cells will be quickly replaced. When you rub hands and say, give me some skin, you ever done that? People used to do that a lot today. But people used to say back in the 70s and 80s, yeah, give me some skin. You're actually giving that person some skin. Okay? Because you're exchanging Strat square. Some surface cells. Okay. This is we said that with stratified squamous, the surface cells are flat, although if you look at the basal layer, they can be a little bit more cuboidal. But you only see a thick layer, multiple layers of flat cells. Okay? So to differentiate Strat square from transitional and its look-alike, you look at the surface. If the cells at the surface are flat, you're dealing with stratified squamous. If they have not flattened out, if they're more cuboidal or dome-shaped, you're probably dealing with transitional. Okay. When we talk about stratified squamous, we differentiate between keratinized and non-keratinized. Keratin is a tough, dry protein that is produced by certain stratified squamous epithelial cells, like those that line the surface of the skin, the epidermis. In fact, because of that, we call those cells of the epidermis keratinocytes. They produce keratin. And what happens is, as those keratin-producing cells move closer and closer toward the surface, they begin to die. So the nucleus breaks down, organelles disintegrate, and you're left with a bag of keratin that line the surface of that epithelium, the epidermis. Okay? And that layer of keratin is protective. It helps to protect physically as well as from chemical injury. Okay? Because the cells are dead, you don't see any nuclei. You just see strands of this keratin made up of these dead cells lining the surface. Keratinized stratified squamous is located in areas of our body that are dry, like the skin. So it says keratinization transforms the cells into non-living protinaceous material which remains attached to the underlying cells by tight junctions, okay, by some type of anchoring junction. And that keratin layer is strong, it's flexible, it provides physical and chemical protection. So if we look at, and this is a high power view of the upper part of the stratified squamous epithelium, you can see that the cells are flattening out and then they're losing nuclei. You see these strands of keratin along the surface. Now, you see a lot of space here. Some of that space is artifact, meaning that in preparation of the slide, the tissue begins to separate. This is all keratin. So this is keratinized stratified squamous. In other parts of the body, where you have Strat square, like the esophagus, where the surface is moist, you don't see keratinization. So that would be non-keratinized stratified squamous. So a non-keratinized stratified squamous, you can see the nuclei all the way up to the surface. So you know this is non-keratinized. Stratified cuboidal, sweat glands, okay? Developing follicles and the lining of larger ducts, the lining of the the ducts of certain glands, but they're the larger ducts, so like mammary glands, sweat glands, salivary glands, pancreas. Here, in stratified cuboidal, you see two layers of cells, okay? And the nuclei are more rounded here. So that's why we call it cuboidal, or here. Again, you base the appearance upon the surface layer of cells, the way that it's facing the lumen here. This is a large duct. Here is a large duct from the parotid gland. Again, you can see two layers of cells, so stratified, and the nuclei here along the surface are nice and round. So this is a cuboidal. Now, stratified columnar. This is the least common of any type of epithelium. This is the one you're least likely to see. You see a small amount in the pharynx, in part of the male urethra, and if you have some really big ducts traveling from glands that are part of glands, then sometimes instead of stratified cuboidal, they can be stratified columnar. So this is part of the male urethra here. And you see this basal layer of cells here, okay, and then you see a surface layer of cells here that have oblong nuclei. So this is stratified columnar. Let's go to pseudostratified. Let's talk about the characteristics of pseudostratified. We said one of the major locations is along the respiratory tract. Okay. It is typically ciliated and includes goblet cells. Now that's typically, it doesn't mean that all pseudostratified epithelium has goblet cells, but in the respiratory tract you will see the cilia and the goblet cells. We talked in AMP about it being responsible for that mucociliary elevator, or some people call it an escalator. So what happens is this. This epithelium secretes mucus that lines the surface of our airways. And as we inspire or breathe in air, if it contains dust, the dust sticks to that mucus. And then the cilia propel that mucus back up to the back of our throat, where a couple hundred times a day we swallow, or we might cough it up to remove it. And so this is kind of a diagram of what pseudostratified is. You see multiple layers of nuclei, but every cell here is touching the basement membrane. Here you see goblet cells, and there are your cilia. This is a real pseudostratified columnar epithelium. And to me, cilia look like little hairs. They're not actually hairs, but they look like that. They're scraggly. There's a goblet cell. But you can see that each cell is actually touching the basement membrane. Sometimes it's hard to see it, but that's the case. It's really a single layer of cells, although the nuclei are little stratified. And we said transitional epithelium lines the urinary collecting system. Okay, so it's going to line hollow organs that can stretch or fill. So it begins with the calyces of the kidneys, it extends into the pelvis, the renal pelvis, the ureter, the bladder, and the proximal part of the urethra. All of those structures are lined by transitional. So it says when the bladder is empty, the epithelium is at least 5 or 6 cells thick. All right, the dome-shaped cells at the surface. When the bladder stretches, the epithelium is only 3 to 4 cells thick. They glide past each other. Okay. And then the cells, the superficial cells, don't become quite as cuboidal. They thin out some, almost becoming squamous. Okay. So here's a transitional epithelium. And notice that the cells at the surface have not thinned out. This is stained to show the basement membrane. This is the lamina propria. With transitional epithelium, you will often see folds in the organ, in the lining of the organ, particularly when it's non-distended. Not fold. Okay? On the other hand, when that organ stretches, when it becomes full, those folds are gonna disappear. Okay, it's gonna become more like this. But again, you can see kind of these dome-shaped cells here. They're not flat. Okay. We'll just take a little personal break. We just have to take a little break. We all have to take a little break from time. Katharina, is this okay with you? If I just kind of walk a little bit. You'll notice by the way when you look, this is important in clinical medicine, is to examine someone when they're first walking into the exam room. To take notice of their gait. Like this is my gait, okay? But you'll notice different people will have different types of gait. If you look at someone with Parkinson's, it's more like this, right? If you take a look at someone who may have had a stroke on the right side, it might be something like this, right? So it's always important to look at someone's gait. It's part of their gross appearance. We're calling it a physical exam. Nobody here is taking physical. Josie, you took physical exam. Okay. So just throw that out there.
I don't think we got to see Katie's uncle's gait because he was on video.
Yeah, that was, it's difficult anyway because we're kind of filming it. It's better when you have people in person. Because then you can ask them to do more things. When you have someone with Parkinson's, you want to ask them to not only walk, but to stand and then sit. See how they move. Like people with Parkinson's have difficulty turning. For instance, watch this. I turned like I was on the runway. I'll probably notice I was pretty slick, right? Okay. But someone who's got Parkinson's, when they go to turn, they're turning on block like this. They don't do it nearly as well as I just did. Okay? If I wanted to, I could have just kind of done this. No problem at all.
Okay.
I'm good that way. I'm good. All right? But not everyone can do that. Not everyone can do that. And you'll notice that as people get older and sicker, and their gaits change quite a bit. Yeah. And then some people naturally have just funky gaits. Like some people have like high stepping gaits like this, which is weird, right? Or some people who are pigeon-toed walk like this. You know, you see lots of strange things out there. That's one of the beauties of medicine, is to see the variety that exists.
Kylie has a weird gait. Like she likes to walk on the ball of her foot. She's on her tiptoes all the time.
Right. Well, that's kind of what people who are pigeon-toed do, like this. But there's quite a variety of different things. If people who are unsteady, including toddlers, by the way, they take on a more wide-based gait like this. Okay. So someone who's had syphilis that's affected their spinal cord, and they lose proprioception, they'll do this. They'll walk like this. Spots of syphilis, by the way. All right. You know, you have to be in good shape to teach. I don't know if I told you this. You realize I'm probably walking a couple of miles in class. You realize that, right? Ray notices that right away. Kelly, you may not have noticed that. And the other thing that's weird about this class is we're all wearing masks. Okay? So I could be very angry looking right now, and you wouldn't know it. I could have a big old smile, somebody would know it. Okay? I could be mouthing something to you right now. You don't know it. Isn't that weird?
When we first started wearing a mask, I would do that thinking, like, if we were talking about something and nobody wants to know, I'm sitting there mouthing and I'm like, my other surfers are like, Josie, we can't see what you're saying. I'm like, oh. Yeah, that is true.
Right. Oh, the other thing, couple things, by the way, is I do this. Remember to keep your mask up above your nose. If you see me let my mask fall, just say, don't report me to the provost, just say, keep your mask up. All right. It's easy enough to do. If you see, and this was on the lockdown browser, for instance, let's suppose that someone comes into class next time, and they sit right here, or right next to you. What is your proper response? That was it! That was it. You don't need to curse them out. You don't need a lot of capital. Just an, oh, can you sit, you have to sit a little further away. Yeah. All these rules now for the COVID crisis. It turns out that bandanas, and some people are wearing these, they call them gaiters, or bandanas that are just cloth. At first we thought those were good, but now it turns out they can make the situation worse. By the way, when I first started going to the grocery store, it took me a long time during this crisis before I would go to the grocery store. My wife and I were ordering through Instacart. You know, done that? Someone goes to feed groceries for you. And that was a pain. And so eventually we got to the point where we said, okay, we're going to take the risk. We like double masked. We went to the grocery store. I think that at this point we've become a lot more lax. In the beginning, when you heard all these people were dying, we took a lot of precautions. Ray, are you still working at Home Depot?
Mm-hmm.
You got to be careful, because you come across a lot of people. The key is to avoid extended contact with somebody at close range. Even when we come, it's okay if I come and look at your microscope, okay, and I'm there for about a minute or two. It's not okay, but the concern is that when you have like 15 or 20 minutes of contact right up next to somebody for a long period of time, particularly if they're not wearing a mask, that's where you get in trouble. I don't shake hands anymore. Y'all shake hands?
Oh, rub elbows.
Yeah. You can do the elbow thing, just say hi. Usually on the first day, I have everybody give the sign of peace. We didn't do that today. Although we could have done kind of a virtual. We could have done like, just off the sign of peace, or if you want to do like that, or just thumbs up, whatever you want to do. But my concern was that people would be tempted to touch each other. All right, I guess we gotta get back to class. Okay. Just like within our body, we have a skeleton that gives us a certain shape, structure, support. Cells have a cytoskeleton that are made up of different proteinaceous fibers. And these elements of the cytoskeleton come in 3 different types, based largely upon diameter. The thinnest of these fibers are called microfilaments. Next in line, these are these intermediate filaments, and the thickest and largest of these cytoskeletal elements are called microtubules. And the structure, you can see here that the molecular structure is a little bit different as we go from microfilaments to intermediate filaments to microtubules. But they all help to give a cell both its shape, its structure, and they provide support. Sometimes these elements also play a role in connecting or anchoring 2 cells together. Sometimes these structures play a role in movement of materials across the cell, or in movement along the surface of the cell. For instance, they can play a role in the operation of cilia. So the framework of the cytoskeleton is made up of either microfilaments, intermediate filaments, and/or microtubules. Those microfilaments are typically made up of the protein actin. Heard of actin before? It's present within muscle cells. Okay? And actin forms little subunits. Like this. They kind of aggregate and form helix, a double chain like this. I showed you before. Okay, so this is what actin does. It forms this little double helix. And these are the thinnest of the different types of cytoskeletal elements. Okay. They're involved in muscle contraction and intracellular movement. And it helps form the cell. It helps form the cell's cytoskeleton. Intermediate filaments are a little bit thicker. Okay? And they do some of the same things, but more than anything else, they help the cell to resist tension, stretch, pulling. Microtubules form cylinders made up of the protein tubulin. Now they do the same thing as the others. They give support, give the cell shape, but they're also involved in movement. We'll talk about that a little bit later. So you can see that microtubules, these molecules of tubulin, orient themselves so that there's a tubule here that's formed. Okay. In fact, just to talk about microtubules, when a cell undergoes mitosis, remember what happens is it sets up a spindle. Okay. Inside the cell you have a little spindle where the chromosomes will line up along that spindle. Well, the spindle is made up of microtubules. Okay, and along that microtubule, these chromosomes will split and then move to one side or another. So again, it allows for the movement, in this case, of chromosomes. Another part of epithelium is junctional complexes. These are structures that link neighboring cells together, and it can also serve as a barrier to passage or diffusion of substances between cells. Okay, so we're going to talk about three different types of junctions. Occluding junctions are also called tight junctions. They're located along the apical surface of cells. So we have two cells here. Tight junctions would be up here. And one of the things they do is prevent or limit movement of water and molecules between cells, like this. Okay? To help seal off that space between cells. Anchoring junctions are located along the midportion of the cell like this, and they're along here. And they provide structural support. They help to anchor cells together. Okay, so that they're not pulled apart. And then you have a third type of junction that's located more near the basal surface called communicating junctions. Another term for these is gap junctions. And these are structures that allow molecules to pass from one cell to the next. So these little passageways. So, occluding junctions up here, anchoring junctions, and down here would be those gap junctions. They're communicating junctions. Notice that the occluding junctions form like a belt that connect one side of the cell to the neighboring side of the next cell. Okay, whereas these anchoring junctions are little spot wells. Again, they're showing you here occluding junctions, two different types. One's called a zonio occludens, the other is actually this zonio occludens is the occluding junction, the zonio adherens is part of the adherent junctions. Anchoring junctions. So again, occluding junctions are near the surface, the apical surface of the cells. And basically what it is proteins from one cell, these are transmembrane proteins that are extending into the membrane of the neighboring cell. And it's tending to hold the two cells together, and it's eliminating the space between the cells so that materials, molecules can't pass through that intercellular space. That's an occluding junction. Also called a tight junction. Anchoring junctions Have different types: zonal adherens, desmosomes, hemidesmosomes. The zonal adherens generally sits just below the tight junction on the zonal occludes. And what it does is it has these little transmembrane proteins that are connected by these linker proteins within the intercellular space. And notice that these transmembrane proteins are attached to these filaments, these microfilaments made up of actin. And so it helps to keep these two cells joined together. Now, the desmosomes and hemidesmosomes have little plaque-like proteins just inside the cell membrane that are linked to intermediate filaments. And on either side of the intercellular space, again, there are proteins that connected to plaques. This would be a desmosome. A hemidesmosome would be a similar structure that's connecting the basal cell membrane to the basement membrane. These are communicating junctions, or gap junctions. They're like cylinders that allow passage of ions and molecules from one cell to the next. Okay? These individual units here within each cell are called connexins. So again, the idea is that these junctions help connect cells together, anchoring cells together, and oftentimes they're connected with the cytoskeleton. Earlier I said that people use the term basal lamina and basement membrane interchangeably. The basal lamina is a sheet of organic molecules, including collagen, which is actually synthesized by the basal layer of cells. If I have a basal layer of cells that make up a central epithelium, for instance, these cells are actually secreting these organic molecules upon which they rest. You have this layer of organic molecules that serves as the basal lamina. Now, you can't see a basal lamina by light microscopy. It's too thin. You can see it by electron microscopy, okay? But you can't see a basal lamina by light microscopy using a regular microscope. Now, the term basement membrane refers to the basal lamina plus the superficial layer of the lamina propria. The superficial layer of the lamina propria has a special name. It's called the reticular lamina. Okay? And this is the basement membrane, therefore, is a little thicker. And therefore, a basement membrane can actually be stained and can be seen by light microscopy. So if you're seeing this layer by light microscopy, it's truly a basement membrane. It's that thicker structure, whereas the basal lamina can only be visualized by electron microscopy. It's actually thinner. It's a part of the basement membrane, but in and of itself, it can't be visualized by light microscopy. So there's a difference between these two terms, even though in most cases you hear them used interchangeably. Here, the basement membrane has been stained. I'm calling it the basement membrane because you can see it by light microscopy. So here's your stratified epithelium. This is a transitional epithelium now. This is from the bladder. Here's your basement membrane. Here's your lamina propria. Okay. Let's talk about apical surface modifications. These are modifications to the apical surface of cells that help the cell perform a certain function. One type of apical surface modification is microvilli. Microvilli are simply finger-like extensions of the cell membrane, like this. So the apical aspect of the cell membrane is more folded. Okay? The purpose of microvilli is to increase surface area. So you find in microvilli where cells have to perform absorption. So it's easier for molecules to microabsorption when you have more surface area. As opposed to a situation where the cell membrane is flat, like this. This provides less surface area than does this. Under light microscopy, you can't see the folding that occurs. You can't discriminate each of the microvilli. But because of the larger amount of cell membrane along the apical surface, this area stains a little more intensely. Okay? So oftentimes we refer to this as a brush border. So if I ask you what is the apical surface modification that you see here, you can either refer to this as brush border or microvilli. It appears very homogeneous. And again, you find a brush border where cells perform the function of absorption. So in the small intestine, you see a brush border. The renal tubules that have to absorb filtered material, they have a brush border or microvilli. Cilia, all right, so this is a brush border. It's very homogeneous. It looks like a band that's crossing the apical surface. Another apical surface modification was cilia. Cilia are what appear to be scraggly hair-like projections. They're really not hairs at all. They just look like that. They look more scraggly. Okay? These are cylindrical structures that project from the apical surface of the cell that are capable of coordinated movement, wave-like movement. So they can propel, like an egg here, propel it from one area to another. Or along the respiratory tract, they can propel debris within mucus back up toward the pharynx. Okay? So they're capable of propelling. Now, if you magnify one of these cilia, okay, it actually looks more like this. Like a cylindrical structure. And extending into that cylindrical structure are microtubules coming up from the cell like this. Okay. And it's the movement of the microtubules that allow the cilia that wave-like movement. Okay. Now, we said there are microtubules. If you take a cross-section through this cilia, you'll see a 9+2 arrangement of microtubules that will demonstrate just a bit. So this is an electron microscope view of cilia. You can see these microtubules coming up. If you cut into cross-section, you can see 1, 2, 3, 4, 5, 6, 7, 8, 9 pairs along the periphery and one in the center. You have two tubules in the center. So